Good morning. Well, it's about Chinese New Year, so Happy New Year. So it's gonna be a year of a dog. So we should have a very, very pleasant Chinese New Year. Okay. So today is very, very special. We have a very important talk before the Chinese New Year, and invite Professor Zhang Tong-Yi. Yeah. And from my record, Professor Zhang Tong-Yi was graduated in 1985 in University of Science and Technology, Beijing. And during 1993 to 2015, he has worked in Hong Kong University Science Technology. I think it's about 22 years. Yeah, exactly 22 years, long time. And then he retired from UST and joined the Shanghai University. And also he funded the new Material Genome Institute in Shanghai University, and also later fund the Shanghai Material Genome Institute for the whole Shanghai city. Yeah, as the founder and also the dean. And so his research including like mechanical property of materials, micro narrow mechanics, surface stress of solid, fracture, thin films, microbridge testing, and thermodynamics of materials, diffusion, phase transformation, and phase field simulation. So all very familiar for our materials people. Yeah. And he has published many, many papers, more than 250 something. Yeah. So, and also he's been is a well-cited author, and he was the vice president of International Congress of Fracture, called ICF. Okay, and for from 2013 to 17, and he's now the special committee chairman in ICF, and also he has been the vice president of Far Eastern Oceanic Fracture Society from 2001 to 2016. So he's very famous in this fracture mechanics area in the world. And also in 2001, he has been awarded as an ASM fellow. And then 2003 is awarded as the senior fellow of Hong Kong Crutch Foundation. Yeah. Okay, sorry, okay. And then very important, 2011, he was elected as the Chinese Academy of Science as an academician. And later in 2012, he has been elected as a senior research fellow, the fellow of Hong Kong Academy of Engineering Sciences. And later in 2013, he has been awarded as a ICF fellow. So he's got many fellow academicians honors, and also he has been in many editor-in-chief of different journals. For example, like Fracture Continuum Mechanics and like China Technology Sciences. Yeah. So I think he's the editor-in-chief right now. So it's, remember, if you want to submit paper to this journal, you probably get some benefit if you. Okay, so today is a great honor that we can invite Professor Zhang to come to CDU, IAS as a distinguished lecture on materials genome initiative and materials informatics. So let's give a warm and big hands to Professor Zhang Tong-Yi. Yeah.
As I mentioned, they say CT and me, we used to be say associate chief editor. Okay, but now starting from this year, I become the chief editor. So I have to promote, you see, this journal. Okay, CT actually organized a special issue on high entropy alloys. We will publish that, you see, very soon. Okay, we really say appreciate it. Thank you very much, CT. Okay. So now, today my talk is about this materials genome initiative and materials informatics. Roughly say 2.5 years ago, when I decided where I had to go, okay, when I returned to mainland China, I get this invitation from Professor Xu Kuangdi. So now I discuss with CT, okay. So I go, because I never think about I will go to, say, Shanghai. Then CT told me, okay, Kuangdi invited you, how you can reject that? So that's why I say I make my decision. Then I went to, say, joined, say, Shanghai University. Up there, actually I signed the contract. It's on 1914, okay. So when I signed, then they, at that time, only person, then the Shanghai University announced, okay, the MGI Shanghai University is launched. Only one person. So I have to say, read the recommendation letter to the president of Shanghai University, recommended two of his colleagues, okay, to be my one is a deputy associate dean and other associate dean. So now I have a 1 year's transparency, 1 year transparency time. Then in 1915, I 4 times moved to Shanghai University. And also, as I mentioned, we also established the Shanghai MGI. That is the first MGI supported by the local government. Now, city just show me, okay, Shenzhen will put a huge amount of money, okay, on MGI. Okay, I think I say now it's good to say Hong Kong scholars, to Hong Kong people. Now you have a lot of financial support. Okay, don't worry about the money anymore. Now talk about very briefly introduce what is MGI. So MGI actually is announced by American President Obama in 2011, okay, as I mentioned here. His purpose is he put this here. This is a logo of there. Okay. He said, okay, the core is a computational tool. They want to say okay, emphasize very much competition, okay, in materials development. Another he calls experimental tools. Then also called digital data. This should be open to the public. Now I call that a database. Okay, database. That's why comes materials informatics comes. Okay. So basically he want to develop new materials at half time and with only half cost. So now we call the two half. So in China we on this is a direction. We move very, very fast. Actually, I think now in China, the Chinese government have put more money probably than the US, okay, on this is a topic. That is in 2011, in December, I joined this meeting. We usually call it Xiangshan meeting, okay? So that is in Xiangshan, it's in Beijing. So we have a tool, okay? I call them is a super academician. They are all one is professor is Si Changxu, is this. He passed away 2 years ago. He also very good friends of CT. Okay. Another is the professor is Xu Kuangdi. Though that is him. It's him. He invited me, okay, to Shanghai University because he used to work in Shanghai University. But from there, he get into the administrative, okay, to the government, okay, and take all the leadership, okay. This tool, it's still there is really the leaders, okay, in China, especially in the materials area. Without them, I don't think the materials research and development can develop so fast, okay. They really play a very, very important role, okay. They taught to those central government to get a huge amount of money to support materials research, okay, materials research. So after this is a Xiangshan meeting. Now we give this conference that we call a systematic materials science engineer. Then we finally we reached that. I personally also attended this meeting. So we reached 4 topics. We said that we should move forward in mainland China. So one we call is a MGI database. So that we put here. We put we should build up, okay, national wide, and the bigger is a database there. We should say develop computational method and also software. Okay, now because currently we use most software, they are developed in Western countries rather than say in China. Okay, rather than in China. Now we should say put a high throughput materials preparation and characterization tools. That is one of this. We call it in Chinese. We call it platform. Okay, maybe call it a facility. Actually, the facility in Shenzhen. Now you are say CT just show me those major facility will be say in the southern say science and technology. Okay, in Shenzhen. Okay, it's located out there. Now, meanwhile, we want to say select some specific materials as an example. Try to use this MGI approach to get a breakthrough. Okay, actually to get new materials. Okay, get new materials. That's its purpose. So in the US, after 3 years, you see this announcement MGI. That is in December. It's 2014. So the US is published another they call strategy plan. Okay. So now in this they put 4 strategy goals of MGI. One, they put that this is the research culture shift. Okay, basically you have to shift. You cannot use the traditional that is the approach. You have to use this new approach. Okay, new approach. So they are emphasized very much. This is a strategy plan. The integrated experimental computation. In here, they emphasize very much again theory. Why do you need a theory to develop that? Okay, thank you. But I need a boss. So basically, they have to facilitate the access of its materials data. Okay, so that means we want to build up this is a database should be open to public. Okay, if everybody want to use for your materials design, you go to those databases, you search that, you get the information is starting from out there. Then you don't need to repeat. Okay, to repeat the same experiment or same calculation. Another is related to us. Okay, is we have to create a next generation materials workforce. This talk about the education. So for this is a purpose. So 2 years ago, I applied a new UG program. We are never out there. Okay, I think probably in CTU you should also do that. Okay, I don't know. Sherry is here. No, physics. Materials is you. Okay, the materials. So I apply for a new UG program. Originally we call MGI program. So finally, all those after they approve that, they say the title is not good enough. So I changed the title. Then in the new title, we call that materials design, science, and engineer. Because in the new UG program, we have to educate, our UG students, talk about high throughput experimental, high throughput computation, and also talk about database, talk about the machine learning. Okay, so no, it's here. Okay, but that's we have to do that. Now, that is in the US. We now in practice we always put there called high throughput is a computation, high throughput is experiment. Talk about digital data database. Now this is they call MGI in China. Okay, they put all basically the same. Okay, basically the same. So now I would like to mention that another we want to talk about the materials informatics. Okay. Though I talk to Sun Dong, I don't know too much about that part. Okay, if I make something wrong, please correct me. Okay, I'm still learning. The last Chinese New Year, I was visited Poly U. But after the New Year, immediately I learned this. I still read a lot of paper and also books. Okay, I still not know that too much, but I'm still learning that. Okay, I share my experience with you. So materials informatics employs techniques, tools, and theories drawn from the emerging field, data science, internet, computer science engineer, and the digital technologies to material science and engineer to accelerate the materials, products, and manufacturing innovations. Okay, that's the purpose. Okay, that's why we want to do materials informatics. So now, why we want to do that? Okay, the reason is the developers so fast. Okay, so hot area. That is artificial intelligence. Okay, a typical one is we call it all systems Go is AlphaGo. Okay, then you play Go, the machine beat all the human being. Okay, so you cannot do that. Especially okay in last year they have another okay. This is another is okay article also published in Nature. They call mastering the game of Go without human knowledge. Basically, this is called AlphaGo 0. Okay, they use two machines, they beat each other and learn from each other. They finally, okay, no, you see, human being, you see, if you play this Go, you see, you cannot win them. Okay, the machines are so good. Okay, so another one is in published in also in last year. They talk about lessons learned. So basically, they talk about medical doctor, the skin cancer medical doctor. Now this system, they contain a huge database. All your skin image they have stored. Okay, anyone say you have some difference, they put all those skin, human beings' skin's image as a database. Once you have some problem, so they take your a picture, take an image from your skin, then they just compare with those images. Okay, they store in their computer. So basically, that is they're doing that. So now in European country, at least in that paper, they claim that okay, now human being medical doctor cannot beat this APP. Okay, you may have just like your mobile phone. you can examine yourself. Okay, why? So I think about this. Probably I still remember when I was a student, I learned X-ray diffraction. Okay, also including we have to we get a diffraction pattern. We have to use that car to pit one to compete to match whether my diffraction pattern can match one of them. Okay, inside there. That's basically a database, correct? Once they match it, I know, oh, this is a crystal structure, which kind of materials, and so on. Okay, so that is a basic. You think about that is a learning. You have to learn something. Okay, they have stored this. They learn, and as a machine, the advantage is if something new are not inside their database, they can install that. That database is dynamic. It's a continued growth. Okay, you have to think about. So that's very, very powerful. This is published. They call it learning from failure. Okay, so basically they just say, oh, if you have no matter competition data or experiment data, don't think about some data useful, some data just garbage. You want to throw this garbage. You just use that useful data. Ask a student to plot some figure and publish your paper. They said that those you think about the garbage data also useful. They call the fair data. Okay, so why? The reason is they want to use machine learning to build up this boundary between success and the fair. So you have to know where is the boundary. Okay, therefore, those fair data are also very much useful. Okay, so this is basically for machine learning is a classification problem. Okay, so that is those is the developer so fast. But I like this I didn't say comments. Okay, I like this one. So they said okay, this is a physics. To us, we can change that. We said that this is a material science engineer. Okay, to others display you can change that. Okay, so they said okay. Now we have learned that we do research in this area for so many years. We have a lot of experience. We have all tools already there. Okay, so like a CT, so you have rich experience in the material science engineer. You have your approach, but machine learning is a new tool. We don't want to say you get the new tool, you throw away all your original, your experience, your tools, okay? You just get one new. You want to combine them together, okay? So you get a new tool. So that's why we have to learn. This is a machine learning. You put it there, they get a new tool. So this is basically in nature physics, they talk about phase transformation. The human being, they don't know how to determine that. They have to use the machine learning to determine whether they have a phase transformation or not. Okay, that's it. I don't want to talk about those papers, but I like this. This is it. Okay, I like this one. Now the developer is so fast. Now they said, okay, I'm do more mechanics-oriented, they say materials research. So we have to derive some mechanics. You have to derive equations. Now they say, oh, you can use the data-driven discovery of a partial differential equation. So once you get enough data, so you can like the machine to derive this equation, okay? But that is also developed very, very fast, okay, in this area. So I did in last what's the time? Actually, in last I think before last November, I did a search. I use that these keywords is materials informatics. Okay, I use that keywords. I say that the total paper number is not so large at the moment, but you can think about their citation, okay, increase very, very quickly. Okay, I did this in last November. Okay, I did that. Now, how about materials informatics? Okay, basically materials informatics integrates artificial intelligence and material science and engineer. I put this here. They call that domain knowledge. Okay, they call it domain knowledge. So you have to study this iteration. Okay, we have to study you have to done some experimental computation to get some data. Okay, get some data, then you can do a data processing. Then you use machine learning to evaluate your machine learning model. Then you design new experimental computation. Okay, what's the next step? Then you do that. If you reach your goal, okay, you success already. Okay, if you not reach your goal, you do this go through the iteration again. Okay, so here the key issue I would like to emphasize is that domain knowledge means the knowledge of material science engineer, which is the harbor of materials informatics. We cannot just like Sun Dong, okay, you do this for us. Because he does not know too much of material science engineer. He has to collaborate with us. Okay, we have to work together. Okay, that is the key issue. That's at least I know in Shanghai, university, I talked with a lot of people from from this computation science engineer. I talked to them, I discussed with them. Okay, so I found that this is a very, very important. Keep that in mind. Now, talk about machine learning. It's a basic. The rest is a very, very fundamental problem. For one problem, we have to get knowledge from data. Okay, so the data through that machine learning model we get to knowledge. So now this is now if we are trying to understand what's happened, so that is the explanation. If we want to predict what will be happen or will happen, okay, well, that is a prediction. We have to manage that is happening. Okay, that's a control. Sir. That's your area. Okay, this basically machine learning is come from a lot of control people. Okay, a lot of the control areas. But I like to emphasize here, it's not just this. I said the learning can be done by individual human being. Okay, especially something like those famous those professors. Okay, they also learning from those data, but they learning goes through their brain. Okay, especially genius. Okay, all and by machine. Okay, I still put a human being as more important. I will take for example Newton's law. How you get this before Newton? It's actually they have that observation. They have the data, but all the time we don't call that data. That is very clear. You see those all those stars, how they move and so on, okay? You take a look and see those history, okay? So that is by genius, okay? So that's why I put this sentence here. The development of nature science is a continuous, endless progress of human being observe nature behavior and develop learning models and then gain knowledge. So I think that is where is knowledge is developed in such a way. Okay, now put some, say how important is data. Okay, I put some, say, because I'm doing more on mechanical, property of materials, okay, research. So I put all this idea. So I further put there is Paris law. Paris law is talk about fatigue. Okay, how fatigue is a failure, fatigue crack can grow how fast. Okay, this equation looks very, very much simple. It's widely used in engineer practice or in academic research. But the key issue is it's purely a data-driven formula. Until now, nobody can approve that from theoretical point of view to derive this law by use certain model. Still no. Okay, it's purely data. It's from data, but it's widely used. Okay, he just passed away. I think probably last year. Okay, because when I organized this ICF 13, we invited him to Beijing. Okay. Another is this is in Hong Kong in CTU. A lot of people are doing this kind of research. We talk about the Hall-Pitch equation. Hall-Pitch equation talk about those green size on the strings. Okay, they are correlation. Okay, they are correlation. Of course, now we have a inverse Hall-Pitch equation. I don't want to talk about that. Basically, I don't emphasize very much. So those equations, when they develop that, it's basically on data, no theory. Once they get this equation, now some theoretician at that time, because the dislocation theory has been developed, then a lot of people use the dislocation theory explaining what's going on. Then now in the textbook, you can see that based on dislocation pair-up, we can derive this equation. Okay? Don't know the key issue I addressed that is related to machine learning. So when you know if this is one of the strings, or will be called flow stress, okay, you know that is a green size. But how do you know? Together, you know there is a functions. But how do you know they have this form? How to determine this? That is things I have to emphasize. Okay, it's not very easy. You know y is a function of x, but what is specifically form of those functions? Okay, analytic form. Then you have to think about that. Okay, that is not very easy. Another, but though the materials informatics develop so fast, especially in those people who are doing first principle calculations. They're very, very fast. That's why I put it there. This is Ram-Ross's rule. Still in our textbook. I believe so. Still in our textbook. So they talk about, they say, if A and B, two elements, if they form, say they merge together, whether they can form is a solid solution. Okay? So now, what is the A element, what is the B element, they want to generalize that. Okay? They don't want to specifically talk about, say, this is a gold or this is silver. They don't want, they want to generalize that. So in general that, they put that very much one is atomic size factor. Okay? They want to say one atom, if there is we can roughly calculate their size. Okay? Though they are if their size is smaller, difference is if they're larger than that, they will not form solid solution. If smaller than this, then they will form solid. This is now in our language nowadays we call internal stress field or internal strain field. Okay, basically it's internal strain energy. Okay, so now we know that. So the second one is the electron chemical factor. They basically those are two elements, whether they want to form a compound or they form the solid solution. Especially in you are doing, say, high entropy alloys, you have still to ask this question. Okay? So now, this one, they just want to say if there is a electron chemical factor, okay, for the two is element, if they are very close to each other, they would like to form solid solution rather than compound. Okay, that's it. Another is relative is a valence factor. Okay, so whether this, if they are equal, then they can keep that in mind. This one still is a purely data driving the rule. Okay, this is a rule. Okay, it's a data. Now we are understanding more and more. Okay, of course, what's going on. People still say want to do some modification. Okay, on these parts. Still now have some publications on there on this side. So this talk about how to generate. Use that I want to mention those feature. Okay, that is it's at the atomic and the electronics level. Okay, that is the feature. Okay, that's why I said especially in those people they are doing for the principal calculations. So now talk about some machine learning. Okay, that is something I copied from one is my colleague, and still now he's my colleague again. Give you news. Okay, now Wang Lixin is now working with me. That is in those areas. I invited him to join me. Okay, to do this. But now, basically, in machine learning, they call this is called a black box. Okay, so you have a input variable, you have output is a variable responses. You do call this, but there you have some handling variables. You don't know what's going on. Okay, so now if you write down their correlation, okay, now you may write down this. This is okay an intrinsic area. This intrinsic area to some system could be very, very big. For example, stock market. I know my wife complains with me. He said they say before the drop, he want to sell out some stocks. There's some share. Okay? She plays this one, but I don't care. I don't play. No, but this one, if we talk about the finance and economic people, this area is very big. Why? Because you don't get enough information. That's my personal understanding. Okay, if you get enough information, then you can predict. But you never get that enough information. That's it. So that's why it's very easy. This one is get this from there. I get from Wang Lixin. Okay, I don't know is it true or not. Okay, he's writing a book on this. Okay. Now, but in our science and engineer area with well-controlled experimental computation, we can like this approach zero, get smaller and smaller. Okay, but some area are always there. Okay, you have to keep it in mind. Okay, keep that in mind. Now, so that's it. We do is analysis. Okay, so there is you want to get there. So this is then you can say basically separate the area. Okay, in another two parts. If we don't talk about the intrinsic area, one is they call bias, another they call variance. Okay, this is related to the search space. Okay, sometimes they call feature space, but actually that's why I say two critical issues. Okay, I want to mention this. So this one, I give you a lecture as one example. I said, okay, if some boy, one found here another a lovely girl. If he only search, okay, inside his classroom, then he know everybody, he get the information. But those girls in his classroom may not like him. That's a problem. Okay, so he have to get a large search space. For example, the entire Hong Kong, maybe even bigger. Okay, but in that case, his information is not enough. Too large space. Okay, very sparse that is data information. So that give you, they call this a bias. You have to determine how to minimize, to balance this. Once you get that, then you use your model, then all the machine learning model to get that we call it variance. Actually, talk about everything, talk about error, okay? So, correct or not? If not correct, please correct me, okay? Okay, now, basically, everything you know is the data. You don't know the true results. You don't know the true solution. Everything you know is the data. So now the key issue is how from those data you get their correlation. And also keep that in mind, this dimension, when I draw that, is two-dimensional. But really there's a high dimension, okay? It's a it's a high dimension, okay? So now they have another three cases. One we call those underfitting. If you are fitting that, it's not good enough. This usually we call that. Another is from fitting point of view, it's very good, but we call it that is overfit. Overfit, that means your model don't have this capability to predict something. Okay? So usually you get this is your data set. You separate your data set into two subsets. One you call that a training set. Another you call is a testing set. So if you make your model very complex, then your learning training area will get smaller and smaller. Okay? But your testing area where reach a minimal, then will increase. So usually you check very well at which part is the best of your model at this point. This is I copy from a English textbook. Basically, they talk about the same thing. Okay? They talk about the same thing. So now I have to put this here. In my personal view, we have two critical issues in machine learning. One, I call that feature selection. We use which things, okay, parameters input as your feature. Okay. Another is your search space selection. Then you have to determine how large is your search space. Okay. Sometimes people call that a feature space. To say that is a search space. Okay, you have to keep that in mind. Okay. So now I put it there. So this is Shifley. I invite him. I don't know if city remember in Ningxia to get this materials Congress. Okay. I invited him to give a plenary lecture. Okay. He is a for the principal calculation person. Okay. But his group is the one of the largest group in the world. Okay. He built a center and also have a database of there. So he published one paper. They call that the critical rule of the descriptor. Basically, if that, you can find that they use a different terminology. One called features, another called descriptors, attributors, and so on. So I don't know, there's a very subtle difference. That's is their room. In me, they're all the same. Okay, basically, they're the same. Okay. So now, in magazine base, as I see in almost my whole life, okay, before I joined the Shanghai University, in Hong Kong University, what I'm doing is a magazine based. Okay, we have to do derive some equation, okay, to explain the results. So those derivatives are well defined. I know them, they are variable, okay, and also most of the time it's independent variable. I can find their correlations, okay. Those tactile properties, okay, is explicitly or inexplicitly expressed in terms of those variable descriptor, okay. So this expression could be analytical or non-analytical, doesn't matter, okay. Even numerically, it's also fine, or by figures, also fine. So those derivatives are called variable, but mathematically. So we call in the magazine-based formulation and modeling. Therefore, it is very much straightforward to identify whether those variables are independent or not. Okay, that is very much straightforward. In our experiment, sometimes we know that. Okay, that is a feature of variable. For example, we change the temperature. Okay, temperature is one of the variable. We change pressure, or maybe in mechanical, change the loading rate, and so on. So this is well defined. The key issue is you down to the atomic, the electronic levels. Okay, then you lost. Okay, that is still is a big challenge. So in mechanism independent, they say machine learning, the situation is completely different. Okay, so especially in machine learning, first principle calculation data, you have to keep that in mind. And also, now I am asked one of my PhD students, and that's the only one is I get 2 PhD students now in Shanghai. The further one, though, to do that, they say there's machine learning about this concrete is a failure. Okay, then the data scatter is greatly. Okay, now I will mention that. Okay, that. Okay, I will mention. So in this paper, so they are doing say much say they're starting from atomic features or electronic features. Then they do combination. They originally only maybe less than 10. And they combination to do a lot of combination. Finally, in that is a paper, they get is a 4,500 feature candidates. Okay, they get this. When they get this, they use this lasso, okay, to select the best 1D, 2D, 3D features. They are basically there is a job. It says there's original is a classification. This is a 2 features. Now they want to use other features. Okay, then they claim that is much better. Okay, so one of their probably is this person I met is him in Japan. I'm challenging him. I said, oh, what's that meaning? They have really physical meanings of this. For those, each of them, they have their very clear physical meaning, atomic or electronic, okay, at that level. But if you combine them together, what's that mean? They don't know. Nobody knows. Okay, they just combine them together. Okay, combine them together. So that is one thing. This is the original classification by this. Now they separate that because it's much, much better. Okay, that has no question. So now I like this. This is a big guy in Lukman in this area in Los Alamos. Now this is Xue Dazhen. So now he working in Xi'an Jiaotong University. He worked with him for a couple of years, and also for this is also in Xi'an Jiaotong. He also worked with him. Okay, before he returned to China. They published this paper. This paper is their purpose. It's want to do shape memory alloy to try to find the lowest this value of delta T. But they have when you go through feature formation, we know that. Okay, then you doing your measurement, you have a heat flow. Okay, they are not really only one number. That depends on how you heat them, how fast, and cooling them, how fast. So for your bulk, metallic glass, I still think about. Actually, you cannot cooling that. You have to cooling very fast to get your bulk metallic glass. Only you determine these parameters is during heating. If you heat them, you could control your heating rate. Yeah, that is. I read also your paper. Actually. So down there is for this paper, so they try to get the lowest. Okay, that is their topic. Okay, so they have to get something, you get some data, then they starting from there, then they get some knowledge, then they do that. This basically is machine learning. Okay, then they have to design, then they synthesize. They also do another new experiment. Then if they are successful, they stop. Okay, they stopped. So what is the initial data? Initial data is 22. Okay, it's a 22. 22, then they get a feature. They use the 6 features. Okay, they use the 6 features. Then they training their machine learning, they training their model. Okay, after training that, they want to predict what's the lowest, okay, the delta T. Then their search space is roughly 800,000. Okay, but each time they change there is a composition 0.1%. Okay, then you can calculate that. So now each time they recombine data from the machine learning 4 candidates. Okay, then do the new experiment, then go back there, Then if they are reach their goal, they continue. Okay, then they keep that is iteration. Okay. Now the regressor data mining, they use different data mining is software. Now everything is on the line. Everything is basically open. In Shanghai University, I built up a database. All those software are available. You are free to use. Okay, you are free to use. Okay. So the selector everything of there. By the way, also we put Wang Lixin's father is that is also there. We get the software. Okay. We use the criteria that is they have combination. Okay. Why I will write this? Because I personally I don't agree with their feature selection. Okay. So you keep that in mind. So they use the 6 features, everything at the atomic levels. Okay. But you think about it, their search space. Their search space, this is a titanium, okay, that is a fixed. This is a nickel. The only change is this X, Y, Z. Okay, so in most of time, I'm not sure it's absolutely true, okay. Sometimes you do a classification, you have to use this, put it there, not along the same dimension to rise them up, okay, that's it. But here, to a mature scientist or engineer, to me, you need only 3 features. You don't need 6. Because you fix that. Even though you get these numbers the same, if you change it to another mature system, you get the same features number, you may get the same solution. That's my personal opinion. Okay, here I have to address this. That's why I talk about this. Okay, that's starting from there, original 22. Then they do that, they say iteration number. Then to 6 here, okay, they get the lowest. Then after that, they contact still a few. Okay, cycle, they say another 3 times, 3 cycles. Then they cannot get this one, it's lower than this one. So this figure is I copied from their supporting information. Okay, so Wang Lixin cannot say at the time, we really studying this paper very carefully. So there, the key issue is this. When they predict, they say delta T actually pretty high. But they still do, they say, a measurement. They get a very low one. So that's it. We still say on this part, I have to learn. Okay. But especially, I cannot convince this Wang Lixin. I call this Sun Xue. I asked Xue, well, what's going on? He said, because everything you predict something, you always have some errors there. You have a distribution. I will show that. Okay. So now I ask my student to do this. We said, okay, they have iterate 9 times plus the original 22 data. Each they have 4. Okay, each 3 sheet. So the total is 58. Okay, now we have I use all their data. But this feature I only use 3. And also check from there is a feature formation. They can have feature from B2 structure to R structure, or also B2 structure to R19 structure. So I said, oh, we only limit ourselves, okay, to this is a transformation. Okay, this is the mature science and engineering knowledge. Okay, I have to use my domain knowledge. Okay, now here, so I get another 5 data, I don't use them. I get only 53 alloys are data. Now the target is the same. I use the same machine learning tools, okay, as they reported in their paper. Okay. Now I get one thing, so this everything unpublished one. I said, now we use the decision tree. Ask the student to use the decision tree to limit our space. Say there is such a space, because the original space is just too big. Roughly, you think about 0.8 million. Okay, that's too large to me. Okay, so we try to do that. So this is a decision tree based on information gain, which partitions this feature space, or space. You can call feature space or something search space, reduce search space. So now you check a look, on the online, you found that there are so many different softwares. We use that a decision tree classifier. Okay, that's we call CAD. Okay, maybe Sundong knows much better than you can this area. Okay, now we put that. So further we get also our sample is data is 53. So now we put that there. You see they have they call Gini index. Basically talk about they have another I want to mention they call information entropy. Okay, there's another data entropy. Okay, so this is related to that. They have definition. I don't want to say that. Okay, to details. Okay, so we said okay the delta t should be small than that for k. Okay, so why I pick up this? The reason is we want to find the smallest delta t. Okay, smaller delta t. So now this x is copper actually. Okay, x is a copper. So now there you see that the further separator is a copper. Okay, there is a concentration of copper. Okay, so if this one I found this is 13, that is okay. Their values okay. They are always larger than this 4K. Okay, so that is this. But so this one then get out of this. Now we have 40 those data. Now I further do that for this is palladium. Okay, so that's one. I want to get this. I further reduce that those data size. This 5. I say it's useless. Okay, I get this one. Okay, now I have this is totally 35 data. Okay, but in the 35 data there is an outlier. Okay, in that is their composition. Though their delta t is too high, so I just remove. I think that is in machine learning they allow us to do that. We have to do more attention to that. They may something new physics out there, but for this properties to get the lowest delta t, we don't need this data. Okay. So we remove that. Now our data number is keep that is 34. Now we do that. They will use the same. Okay. Supporting those vector regression, and also we use bootstrap because in those one you cannot get this variation. Okay, get this error bar. Okay, you will call that error bar to experiment. So now we get that. We use this leaving 2 out verification. So basically what that means is every time I training our data, use 32 data. Okay, after training I use this training results for that is 2 data, leaving 2. Okay, then you repeat this. Then you finally get all of them. Okay, now we get this, get this data. Now my search space, after training that, our search space gets much smaller. Our search space becomes 18,000 roughly. Okay, so from those that is reported in their publication, Nature Communication. Their error bars are here, but the experiment is get the results is here. But we get this one, we get all this things inside here could be lower than this. But now I talked to Wang Gang. Okay, I said, oh, your experiment cannot do so fast. We are doing machine learning very fast. You have to speed up your experiment. We are facing our experiment is basically not move so fast. So we have not get the experiment results. Okay, that is anyway. That's why we get this unpublished work. They're put there. Another is I get one new student. The new student is I ask him to do on TM. Okay, actually scanning TM noise correction. So basically, you have to find this in your sample, find some parts you can call they have a very unique we call feature. Okay, it's not exact. So this one we have tried to because in STM you can scan your sample, go to what we call 0 degree, go this way, then go then finish. You also can scan in this way. Okay, the vertical we call 90 degree scanning. So now you get 2 images. One image is this one, we call 0 degree scanning. Another image is 90 degree scanning. Okay, to keep this is the same, the 0 degree, 90 degree. So now we basically use image matching. Okay, this is very much similar like a face recognition. Okay, this is now, but this one, the TM one is much more simple, much more simple. Okay. So finally, we develop algorithm, okay, methodology to correct this noise to get much better. This is before that correction, this is after the correction. But there is another issue. Actually, you don't know what's the true image without any noise. Okay, so I have to think about one way, found a reference. So we believe that is true. Okay, so to do this, I asked the students to do simulation. Simulation, we know that this gold is a particle. Okay, then we on purpose we put a noise there, different noise. Then we use our methodology to correct that. After the correction, we get their perfect image. Okay, to improve the approach, the algorithm works. Okay, now we can really put this on the TM. Okay, then do an in situ correction. Okay, do in situ correction. So this one is I mentioned that concrete. Okay, this is also still working going on. So I'm published the work. So I have there is a famous guy. I don't know. This is really in mechanics community. Okay, Bajat is their famous person on fracture and failure of materials or structure. Okay, very famous guy. So he publishes a lot of paper. Then in the two paper, they academically argue with another Professor Hu in Australia. Okay, they on the journal paper, they argue to each other. Then they send the papers, they say to me, they said, oh, Professor Zhang, you are also working on fracture. Then you talk about, they say, read our paper to think about who you would like to support. Okay, I said, oh, and ask the student, do machine learning. So we are doing, we still is working on that. I have not finished. Okay, that's their argument. So this basically the point that is 3 point is binding testing on concrete beams. So they change there top of the size dependent failure. Okay? So there you do that, you think it's a materials constant. Actually, unfortunately, they are not. That depends on the sample size. Okay? I think Yang is doing a lot of small scale. Then you won't get enlarged to bigger sample, so you have to think about that. Okay? They have a size effect. So now we use that. This is the equation. We got all this. So in machine learning, they have what they call YAM algorithm. Actually, it's basically Weber distribution. Okay, they're assuming that they follow this failure if without any notch. They follow this Weber distribution, then we can get this failure probability. But the problem is the data is not large enough. So I ask my student that I put all this data, don't care, okay, this size first. Then do analysis at one shot, okay, one time. So that's why I put it there, everything there. So after there, someone can get this. These are different size, okay. You can see for some size, they only have 3 data, 4 data, okay. So I can get there or follow this Weber distribution. Okay, I can determine there. That's why I ask my former student, Dr. Fula, to get his data, he said to me again, do this. Because when he did his PhD under my supervision, he did a lot of experiments, repeated that. For each, the same condition, he repeated over 50 times. Okay, that's a lot of work. But unfortunately, he lost his data. Now, based on this, we really can think that with a survival probability 90%. Okay, if there are no failure, then we found that, okay, the smaller, the stronger. Okay, then we can draw this conclusion. Okay, now my student is doing, if they have a notch, they have a notch, okay, there, what's going on. Okay, then we have to really think about that, we develop. So another is, the work is, when I write down this paper, 2 papers actually. Now this year is where I joined with Professor Shi, another paper will be published. But when I write down that, I have to be very, very careful. Because a lot of my friends, okay, we're also in this community, okay, they are using a different approach. When you say, well, actually my student, they say they get this data, they draft the paper. When I read that, I said, this is not correct. So you have to redo that. Okay, but that's, now I'm still asking my student to do more is data driving this analysis. Okay, why we know this? It's a power law. Okay, it's a power law. This is really from experiment data. That's why I list here. It's very old. It's a paper. Okay, you can think about it's half a century ago. So we know that then from their definition, we get that it's a string rate sensitivity. Okay, reflected. It's by definition. But here is at the constant temperature. Keep that in mind. So now another is here. If that is true, everything here we can relate that to the power law. Okay, we give this power law. Okay, but at the moment, the temperature effect have not to be considered. Now if we talk about creep, we can talk about the stress relaxation. Now we have to consider this temperature is very important. I'm very happy we are doing high temperature. Okay, high entropy alloy. So we maybe develop more equations. Okay, we work with you under your leadership. Okay, now I ask a student do more experiment. Okay, we have to get enough data. So we ask a student to do all this is at 5 different temperatures. Okay, we put it there. Then we get all these data. Okay, all this data. From those data, I said, oh, now I can write down equation. So no, that is just. So how to write down that? Because it's a temperature dependence. It's usually described by Arrhenius equation. That's our domain knowledge. Our domain knowledge. We know this. Okay. So I said, okay, further write down this Arrhenius equation. Okay. By Arrhenius equation, we have activation energy delta G. Okay. Usually, so when I was a student, we have learned dislocation go through. Okay, those dislocations, those forced. Okay, cut. Okay. Then this is one. By this one, we introduce that we can have this V. The V is called that activation volume. Okay, because your mechanical work can reduce this originally energy barrier. Can reduce when you apply mechanical load. Okay, so that's we can get this one. Okay, so now from there, this is all from experiment data. Okay, you can see that at the difference, this is a mechanical loading. Okay, their strain rate is really depends on that is a temperature and follow this Arrhenius equation. Okay, that's no question. And also the slope from here, you can see that also depends on load, depends on stress. Okay, so basically, well, that's the point. Okay, now get all this data. Get this data, then we get this Arrhenius equation, we get this one. Now the preface that this factor, prefactor, this one, I make an assumption, okay, or hypothesis, okay. I said that they don't depend on temperature anymore. They follow this, power law. Okay, that is very good. So, okay, now I get this. So now you have to keep that in mind that this N primary I put it there, it could be negative. So that when I see some of the people, they say, why you want to get this? Nobody believe you. I have to argue. Okay, I have to argue. Okay, now from there, I get all this. This is from this data. From this data, then propose this equation. So the equation should look like this. Okay, so it looks like this. So now, so this one, so I ask is only to have a 2 limit case. Okay, so one, you think about this, then you follow that definition of M, then you will get this relationship. If this approaches 0, then you have this power law. If this approaches 0, then you can use this relation to calculate your activation volume. Okay, now in the literature, though people only conduct this experiment at 1 temperature. That's why I call them 1 temperature approach. Okay. So they are 1 temperature approach in which experiment conduct at only 1 temperature. Okay, then determine this one, then determine that's fine. But then they want to use the same data to determine this activation volume. That is the original draft the students give to me. So I want to take a look at the mathematically done not work consistent. Okay, because I'm mechanics, I also do a lot of mechanics. I know that the equation. Okay, so this mathematically have some problem. So that's why I ask a student to do more experiment. Okay, more experiment. So now from there, this work is still going on. We want to use this, how many times I still have?
10 minutes.
Okay, 10 minutes, I will speed it up, okay. So I try to because you want to promote this materials informatics. You have to find some model very much simple. Okay, so I ask my student to do what we call one-dimensional toys model. In this model, originally I mentioned that you don't know their correlation, but this model I have to know the correlation. Okay, this is one-dimensional. There is such that I limited this is a region. X is a change from -1 to +1. They have actively say this minimal. So that is a region. Okay, so because they can do a continue, but I ask my student because we want to do really data. I want to get 1,000 data points. Okay, use this equation here to 1,000. So now we use the same different. Now the key issue is how to find this x for minimum is y with the least numbers of cycles. You do the cycles, okay, iteration. If the initial data number is 5, that is okay. Become a machine learning problem, okay, well-defined problem. Okay, now on purpose I get that is initial data distribution is uniform distribute. Another is a bias distributor. Another is a random distributor. That's why I did that. I asked my student to do that on purpose. Okay, now there is a machine learning. I use that is SVR to do this. Okay, then we are found so this is only 5 times. This one is the best. That one. But this is 11, this is 7. Okay, iterate. Okay. So then if I use that for bias distributor, we have a bigger problem. They cannot the global minimalized point. The only found is a local one. Okay, that is a problem. Problem that is related to this. So another is a random distributor have no problem. Okay, if random distributor, then this is 5 times. Okay, so this one, which is machine learning software, is better. That depends on your data. But before you do that, you don't know. So you have to try more. Okay, so that's why now I ask you to do another machine learning algorithm. Okay, to use that. Okay, to use this one. Now this is only 4 times. Okay, it only iterated 4 times. That means this machine learning algorithm is better. Okay, to this data. Okay, to this is a purpose. So now they found those local, but also found the global minimalized is kind of reached. Okay, it's no problem. Okay, only for this one only 5 times. Okay, iterate 5 times they found it. Okay, now use this one in random distributor, even you say 3 times, they can find it. Okay, that is my conclusion. Okay, concluding remarks. Okay, I would like to say it is this one is change. Okay, because I talked to mechanics people also. I saw change it to materials people. So it is urgent to build up those database. Okay, build up. So we have to integrate experimental computation and also theory and data science. Okay, we have to educate our those next our students. Okay, with this artificial intelligence. Okay, so the knowledge from data is achieved by learning of human being. That I put this. I copy that, download from this one online. Or we should put them together. Okay, we cannot just highly say okay only depends on machine. Why do you say all brain also very, very important? Okay, we put them together. That's it. Now this is I got a new building. A city just asked me. So this is okay. Our new buildings here. This is I don't know. They got this picture. This is a picture. It's really there is those photographers got a beautiful picture. This is a new building. This is our new library. Okay, that's the entire building is all MGI. Okay, so again, please support this journal.
Thank you very much. Yeah. So now we have Q&A sections. Any questions from the audience? Yes. Professor Genome. Yeah. Professor Sun Dong's first. Yeah.
Hello. Thank you. Thank you very much for excellent talk. Okay. I'm not the material people, but I did learn a lot.
Yeah, across the board.
I got
joined
a lot
your
of
area.
information from your talk. Okay. Right. Okay. I think this is a beautiful integration of the material science and machine learning, data science, and so on. Okay. So my question is, what's the unique role that machine learning, intelligence, AI, data science can contribute specifically to material science? Or in other words, okay, what's the new change because this integration come to the material science?
Okay,
yeah.
Very, very good question. I'm waiting actually for this question. Okay, so they always ask me this kind of question. Okay, I have to talk about those what's the difficulty or challenge to our materials people to how to use this machine learning. So actually, before I moved to Shanghai, I talked to the department head is in Hong Kong UST, the computer science engineer, computer science. I talked to them, asked they say Professor Zhang to help me. Okay, he said I'm not interested in your area. Why? He said in that such a word, because now they handle everything they call big data. The question is, in material science engineer, our data is not big enough. At least to those people they are working on web, those data on website, on the line, So that is the first is our data, not sufficient, That is one thing. Another is the dimension is very high. And also, if you don't understand the materials, you don't have any materials knowledge, then you don't know how to handle this. Now I travel with those China East airline. Every time when I sit down there, they come to me and say, so they said, Professor Zhang, I know you like to drink, Longjing. Every time they just say, because they have my record, they have the data. But for our materials data, it's not so straightforward. Why do I explain what's going on inside? So I talked to Wang Lixin the same thing. I think you have to think about from your discipline, your expert, So you think about how to handle those data. So notice so many not very large, but the dimension are very high. And also, why to combine, that is another challenge issue. Our chemical composition with this mechanical, is a materials processing. We have to combine them together because a lot of this materials property depends not just on composition and also on processing. Those things had not been solved at all. We don't have this, the best, those algorithms, machine learning algorithm to handle this issue.
So second, actually, you already answered my second question. My second question actually is not data, not learning. I'm talking about the big data and deep learning.
That's correct.
All right,
That's
because
correct.
only big data and deep learning now can really change our world. Such as you talk about AlphaGo and so on, because of big data and deep learning. You already answered my second question. No need to ask. Thank you.
Yeah. So maybe in the back, yeah.
Very enjoy your talk. I have a question about, I think we have a lot of common interest in this kind of, machine learning and research. My first question is, since you have data, right, how can you be sure that the data is robust and reliable? That's the first question. The second question is, you use the model to train. You have to train the model. There are many models available, right? How does one know which one, the best model that fits the data you are analyzing? The two basic questions.
I answer your first question first. Second question first. So actually, when I give this toys model, I want to tell you, all of you, So you have to use a more, machine learning model to handle. You cannot just depend on one. If some papers say this one is the best one, it may not be the best one to your data. That's my point. Even the same problem but the data distribution, on purpose I get 3 data distributions. Okay, they could get different results. So that's why I asked my colleague, when we built up this database for the machine learning algorithm, I put a lot of algorithms there. Okay, so you can do that to use no matter which one. Okay, you use more, then you make a comparison to find which one is the best to your data. Okay, this is number 1. Okay, number 2. So how do you know this data is reliable? Okay, that's a very crucial question, critical. Okay, I told my people there build up this the database. Now we are database developer very, very fast. I told them, we don't care that. Okay, just as you see, when you publish one paper, even though in Nature or in Science, okay, so as long as you get this review process in publish out there, whether you are correct or not, okay, the other people, they will check you. Okay, I like this user to check your data. We give each data one of the this paper DOI. Okay, we know you will have identification. You have ID card. Okay, ID number. Okay, so if more people use their data, they said that data is garbage. Finally, because everything is a computer, the computer will record and says that okay, that is a garbage data. We'll not use that anymore. Okay, so at that, this is the initial stage to develop this database. We don't have this power to repeat all this testing, to repeat all this calculation. We like those users to identify this. Because everything computer, okay, you can put a record there very easily. Okay, that is not difficult at all. Okay, but we just say a database here. I would like to mention it. The database is who build up a database. Who have to think about the rule of your database, the dual database. It's like Web of Science. You don't own this is the right, intelligence is the right, okay, of this data. Who provided his data? That's his data. I will say always market that. If we say everybody like his data, get credits. If nobody like his data, he get blamed. Okay? Yeah, that's why I say I did here. So I did is 1 hour, other layer. I said they put it. You have to pay more attention to that. If some data looks not normal, okay, then you have to pay more attention.
Any other question? Yeah, Mr. Liu. Oh, lady first.
Yes. So my puzzle always is about the impurities. So take concrete as an example. So, the experiment that you did with a particular batch of concrete will have a defined set, which is unknown to, the people who are doing the experiments. But the impurities are there. It is always there, and it is a variable that you cannot account for in your different databases. So how do you, accommodate that? In all your machine learning?
That is very good. Actually, it's a topic I gave to my PhD student. Okay, so I finished that part. If you I'm talking about that part without a notch. Okay, we are assuming that they form this web distribution. Okay, so don't keep that in mind. They all have a size effect there because they have a different size. Concrete is you zoom in, they have a very complex microstructure. Okay, they have a lot of things out there. So now you don't have enough data. So I have to use all their data. With those samples, I have a different size. But basically that's my decision. I think they all follow web distribution. Okay, that's why I argue the same questions. Don't think about that further principal calculation results is really true. It's an approximation. Okay? No exact calculation. You have to keep that in mind. So now in this case, you have, for this one, I give if they have a notch, my idea is, okay, for each one, they have a distribution. I have to take care of this distribution. What that means even, like say, Fran did his PhD thesis, even you repeat your sample, okay, the same sample, same say testing condition, you are notice for those brittle fracture, okay, they always the data scattering greatly. So you have to take care of the distribution, then consider something else. Especially if we in the future we handle say creep, handle you say those fatigue failure. That is very crucial. So I like you say your question. Okay, really is a key point. Okay.
Hi, Professor Zhang. Very inspiring talk. I learned a lot. Every time I attend your talk, I learn something new. Yeah. So my question is, I saw you integrate a lot of artificial intelligence, like algorithm computation. But as an experimentalist, may I ask, what do you think? What is our role in terms of experimental part in this area?
No, I think I say if you really okay, like that's like say I have done this in my career okay for almost my whole life okay. But I have starting say a new career okay in Shanghai. When I really starting this one, I think I say okay, CD they are correct. They want to really develop some materials really useful. It's not like it's mechanics people. They always said, my equation is powerful. Once my equation, my understanding is correct, I don't care whether they can use it or not. That's the difference you have to think about. Now I'm really very serious think about this issue. Okay, we have to develop something that's useful. If you think about this, now you have to say, let's talk about materials design. Okay, so you have to say, I ask my those young colleagues. Okay, they have to starting. I still think HB map is a good for start. Okay, of course the HB map you can say really dynamic. You have new data. You can say really refine those HB maps. But from there you roughly you don't know. You know their area, but you want to determine some parameters. For example, you want to determine either it's a chemical composition or you want to determine the best materials processing condition. Okay, then you have to of course you want to combine them together is more challenge. Okay, so you want to determine that, then you have to do from experiment do initial experiment design to get those initial data. Once you get this initial data, then the next run of your experiment will get from machine learning.
Last question. Okay.
Thank you, Professor Huang. Professor Zhang, thank you very much. Very inspiring talk as well. Actually, can I summarize, because I had this question at the very beginning, but I hold until the last to ask. That's my honor. Can we say we are combining mechanism-based modeling with this machine learning technique, so eventually we can have a better model or better guidance?
That's of course. The answer is but the question is, especially as I mentioned that you will do a lot of materials property. You're doing for the principal calculation. Mm-hmm. You don't have a model.
Yes.
Okay. Mm-hmm. So those people who they are doing, they have to okay, turn to this machine learning. They have no other tool. Just like you say, why this one we get bioinformatics first, but we don't have those equations for life science. If you write down some equation for life science, now you win a lot. You win a Nobel Prize. Okay, they still don't have a no. Well, so that's why I told to mechanics people. Mechanics people said, we can derive this equation. When you do you build up. It's a calculation software. It's based on your equation, your governing equation, continuity equation, and the boundary condition, and so on. Okay, but in real, a lot of cases, you cannot simply just use one equation to describe them. Then you have to face a new challenge. In that case, you have to come there. Actually, when I say my colleague Cai Lilong do for the welding, he uses machine learning. You know him very well. So he talked to me. He built up some model. He want to get his mechanism based. They also try to towards this direction. So if we can combine them together, that's the best. Okay.
Thank you.
Okay. If you do have a question, Professor Zhang will be in the IAS office. The new site of IAS is in Fang Runhua building, 6th floor. Yeah, so the whole 6th floor is our new IAS site. So Professor Zhang will be in one of the offices. I don't remember them. Yeah, he will be there from about 2:15 something until 5. So we have arranged some one-to-one discussion. But if you really want to stop by, feel free to come. Yeah. So let's give Professor Zhang once again a big hands.
Thank
Yeah,
you, thank you. 好 ，OK, Happy Chinese New Year 。给大家拜个早年。
Now we have